So the name of my talk is Re-envisioning generic server architectures for I/O-driven compute. And all of the work that I'm going to talk about here is, of course, actually the work of grad students, not me, particularly Hugo, Nirav, and Zhipeng, as well as the efforts of many senior colleagues. So from the P4 perspective, if you consider the evolution of network programming over the past few years, one way to look at it, which I'll call the P4-centric way, is a progression as follows. First, we had fixed function ASICs, which were configurable but not truly programmable. And then came OpenFlow and classic SDN switches, followed by the modern PISA pipeline, programmable via the most expressive language yet, P4, the crown jewel of the EuroP4 workshop. But for everything that was left, the things that P4 couldn't handle, we threw it to general purpose off-the-shelf servers. And general purpose servers are programmable using classic programming languages like C++, and therefore they're the most expressive. And many important networking applications still rely on general purpose servers because they simply don't fit into the P4 model. And that includes applications like DPI, anything that relies on TCP reassembly, more complex computation, or highly stateful tasks. And unfortunately, I'm going to argue that these networked applications are in many ways poorly matched to the architecture of generic servers as well. When you talk to architects or read a traditional computer architecture textbook, you'll find a number of assumptions about software that are baked into the underlying design. And many of these assumptions have to do with handling I/O. One of the assumptions is that software invokes the network and not vice versa. This statement is a little fuzzy, so I want to give you an example. Consider the memory stack before the introduction of GDIO. The assumption was that the most important data to keep in cache was data that the application already had. Whatever the application was doing was important, and whatever the NIC was doing was not as important. The idea that the NIC might actually know something about what the application needed was only pushed into the architecture with the arrival of DDIO. RDMA is an even more radical push towards recognizing the NIC as having a right to invoke action on the server. The NIC can write into memory without ever touching the CPU. Another assumption is that the CPU is a one-stop shop for processing. When data arrives at the NIC, it has to cross this 10,000-mile wide chasm that's PCIe to get to the real processing. There's an increasing interest in accelerators, and yet all data has to go to the CPU first before it goes to the accelerators. Moving between the NIC and then, say, the GPU requires another 10,000-mile interconnect going from NIC to CPU to GPU. PCIe is often constructed explicitly as a tree, with the CPU sitting at the root of the tree, recognizing the centrality of the CPU in the way that compute is orchestrated. A final assumption is that I/O is rare, that the majority of compute cycles will be spent doing non-networking things. Think of all the optimizations we learn about in the design of processors in the memory hierarchy. All of them are focused on speeding up computation over data that is already resident on the processor. It's only recently that we've started to think more and more about optimizations to speed up receiving or sending data from the wire. Yet in the network functions I referenced, and in a class of applications that I'm about to talk more about called I/O-driven applications, data is continually arriving off the network and demanding to be processed. Every arriving packet is implicitly a demand to invoke functionality. Modern applications may also involve multiple compute platforms, a GPU, disk, or accelerators. And this pushes the CPU into this awkward role where it's an orchestrator, receiving all the data arriving off the network and then triaging it across other processor cores, shipping it off to disk or sending it to an accelerator. Finally, a non-trivial fraction of compute cycles are spent handling I/O in some fashion, and hence we've seen a lot of work lately, for example, trying to offload serialization or transport away from the CPU. So these properties are described are not specific just to network functions. They're specific to a larger class of I/O-driven applications. Consider key value stores, lightweight classifiers, web servers, caches, streaming analytics frameworks. All of these share the same mismatch with the traditional compute model. And for a long time, a lot of clever software designs have just masked this mismatch. and general purpose servers have done okay supporting IO-driven applications. Here are some of my favorite papers from the NFV domain. But it only worked for so long. When I used to review papers, we would see graphs that looked something like this, with throughput on the y-axis and some system configuration on the x-axis. And everybody's papers topped out the link rate. They hit this maximum bar that people drew across the top, labeling it 10 gigabits per second. But then line rates grew, and we weren't consistently hitting them. And now for many applications, the gap between line rate and what the application actually achieves is quite wide. Let me give you some specific numbers. Here I'm showing time on the x-axis and the state-of-the-art link rates on the y-axis. There's a red line at the 100 gigabit rate, although many data centers now are moving towards 400 gig and planning for terabit links. With one 3.1 gigahertz processor core and an Intel E8-10 100 gig NIC, we're able to sustain about 40 gigabits per second. With two such processor cores and the same NIC, we're only able to sustain about 60 gigabits per second. And for a robust application like the Snort IDS, even with 16 3.1 gigahertz cores, we top out at under 20 gigabits per second. Now, I think everyone in computer systems at this point has given up on the idea that CPU parallelism will save us. But just to illustrate why that problem also applies to networking, we can once again look at Snort. So this is a figure from the Snort paper, since I'm sitting here at the Snort, or at the Pigasus. Sorry, this is a figure from the Pigasus paper. Since I'm sitting here at the Pigasus developers group, I assume you've already seen this. But here I'm showing on the y-axis the number of CPU cores required to sustain zero loss, assuming perfect linear scalability for Snort. On the x-axis, I have a range of empirical traces. And the key thing here is that it can take up to 667 processor cores to sustain that line rate. And of course, more cores is a bad idea. It costs more money, more energy, and more rack space. And as an aside, if you're reviewing papers, evaluating new hardware, more cores isn't always a bad idea. Sometimes it's actually the cheapest and most efficient thing relative to, say, a power-hungry GPU. But oftentimes, scaling with CPUs really is just very costly in terms of these human factors like finances, energy, and space. So that brings us back to our poor general purpose server. It's creaking away under this deluge of network data. So in this talk, I want to discuss how we can make changes in I/O in software and hardware to make our general purpose servers a bit more optimized for the I/O-driven use case. In data centers today, we already see the deployment of servers that have somehow been specially configured for the support of, say, file storage or machine learning. And so we want to envision what an I/O-driven server would look like for this special class of I/O-driven applications. And with apologies to Scott Schenker, I'm not going to present anything radically new here. I'm really just trying to distill the big picture from exciting work going on in this space, some, but not all of which is coming out of my own research group. So I'll touch on 3 case studies from my own group: the Pigasus intrusion detection system, the Ensō pipe NIC interface, and COPE. But I'll also give some shout outs to other proposals that I think are also pushing towards a new I/O-driven architecture in exciting and innovative ways. So if you find you're really excited about working in this space, I'd check out what people like Simon Peter, Tom Barbette, Dion Kostic, Minlan Yu, Kyung-Soo Park, or Irene Zhang are doing. Okay, so I keep using this term I/O-driven architecture. What I mean by this is that we need to reorient the architecture of our servers to treat the NIC rather than the CPU as the controller for network processing. And enabling the first steps towards this are the rise of programmable NICs like smart NICs, FPGAs, or these new DPUs, IPUs. Some of the first software systems to integrate with smart NICs identified them as just another accelerator, alongside many other new compute platforms, FPGAs or GPUs, etc. But I think that programmable NICs aren't important just because of what type of compute that they expose. Although we should carefully consider what type of compute we want, and I really love FPGAs, I think the important thing behind the rise of these smart NICs is that they allow us to reorient both the hardware and the software to explicitly control I/O placing the NIC in control of how and where data is processed, and leaving the CPU to do what CPUs are optimized for, servicing the application-specific code. So we first started thinking about inversion of control in my group with the design and implementation of Pigasus. Pigasus targets signature-based intrusion detection and prevention. Signature-based IDS take in rules like the one I'm showing here. In software, resolving whether or not a flow matches a rule can be decomposed into the following stages. First, the packets arrive and are parsed to identify Ethernet, IP, and TCP headers, and then there's the TCP reassembler. The multi-string pattern matcher checks for exact matches against exact match strings that must be found in the payload. Those are things like the string username or get permissions. The full matcher then checks regular expressions like this longer regex here. The Pigasus team wasn't the first to apply FPGAs to the problem of intrusion detection, but traditionally most of the research stuck with the model that the CPU was king, and the FPGA was treated as a subsidiary offload, tasked with optimizing just one or a few components of the pipeline, typically the string matcher or the regular expression matcher. Pigasus inverts this and treats the FPGA-based NIC as the primary compute platform. In fact, the NIC performs all processing except the full match, the regular express processing, and a few other checks. I have a longer rant about why large-scale regexes perform better on x86 than on an FPGA, but I don't have time to go into that today. The key thing that Pigasus achieves is by placing the FPGA first, is that it can do a massive amount of highly parallel filtering over the traffic before shipping it off to the CPU. And it turns out that we can identify 95% of innocent packets as truly innocent right there on the CPU, bypassing, or right there on the FPGA, bypassing the CPU entirely. A mere 5% of packets wind up traveling to the CPU. And furthermore, the FPGA has done another level of filtering not shown here. It's identified that many of the signatures definitely do not match this packet, and therefore that the CPU does not need to check them. Of those 5% of packets, they typically are only being sent to the CPU along about 1.1 rules to check, out of an original 35,000 rules. And while this talk is not about the trade-offs between FPGA and x86, just for fun, I'm going to explain from a 10,000-foot view how Pigasus's filtering works. Pigasus uses both pipeline parallelism and data parallelism. But Pigasus's inner pipeline is a fractal of the filtering that happens going from FPGA to CPU. The first stage of Pigasus checks exactly one match string per rule, and does so with 32 data parallel pipeline parallel pattern matchers. It needs to process 100 gigabits per second. So we have lots and lots of them, lots and lots of small pattern matchers that are just checking one string per signature. In empirical traces, only 23% of packets match any of those single strings. And so we now know that the remaining 77% cannot possibly match any signature. So that 77% is released. And only 23 gigabits per second go on to the next stage, where we check the packet headers. And we do this with 8 parallel replicas. Finally, we're left with 11 gigabits per second of traffic on average. We check the remainder with 16 parallel matchers. These matchers are much more complex than the first two, but we only need 16 of them because we've filtered out so much. The remaining 5 gigabits per second are sent to the CPU for a final check. But at this point, 95% of innocent traffic has been accurately identified as such. This is kind of a silly graph, but it is instructive in how much work the FPGA takes away from the CPUs. Between Snort and Pigasus, Pigasus uses orders of magnitude fewer processor cores, and the filtering on the FPGA is taking on all of that. But what did I say a few slides ago? To decide whether or not this is actually better, we need to take into account the cost of the FPGA. So to see whether or not Pigasus is better than Snort, we have to consider that cost. And that's why measuring power and financial cost is useful. We can see that Pigasus also uses about an order of magnitude, on average about 30 times less energy than an equivalent Snort deployment. And assuming a 3-year deployment lifetime and publicly available cost sheets, we think it would cost about 1/3 as much to manage a 100 gigabit line over 3 years using Pigasus. Stepping up a level, we can consider some lessons from Pigasus. Now, some of Pigasus's gains are definitely micro-architectural. Like I said, I really love FPGAs. But today I want to focus on the macro architectural or system integration lesson. And that is, from Pigasus's perspective, the NIC is a controller and the CPU is basically a regular expression accelerator. And if we extrapolate this lesson to help us envision what a server optimized for I/O would look like, we can come up with a couple of conclusions. In the traditional architecture, the CPU has to receive all traffic and process it, and may choose to delegate to another accelerator. But in a network-driven architecture, acceleration might be performed inline on the NIC, like it is in Pigasus. Going one step further, the NIC might become the controller and direct traffic directly to or from other platforms that are not the CPU. I was really excited to hear about some new work from Min-Lan Yu and her collaborators at KAIST, in which the NIC pulls data directly from disk to write out to the network, bypassing the CPU. You might imagine the NIC shipping data directly to the GPU or another accelerator as well, once again, saving the CPU from having to do this role as the controller of the traffic steering. So our first task for our NIC as controller in an I/O-driven server is to give the NIC the responsibility of steering traffic to the correct worker node for processing. Another lesson from Pigasus is how important it is to try and filter and reduce data. So much of that 100 gigabit per second coming across the wire can be reduced or deduplicated quickly. And this is a running theme across many systems that are dealing with massive amounts of data. We see a lot of discussion about filtering and reduction in big data workloads, things like MapReduce and Spark. So it's no surprise that the networking equivalent should be no different. But in the traditional server architecture, in the networking setting, because the CPU is forced to take on this whole fire hose of traffic, this takes up CPU cycles. And as recent work from Berkeley and Google shows, this also can result in host interconnect congestion, hurting latency and throughput. By filtering on the NIC, we relieve both PCIe and the CPU from this onslaught of data. This is really powerful, even though it's kind of obvious when you look at it. Finally, we should consider interfacing with the outside world. In Pigasus, this is the TCP reassembly and the Ethernet parsing, getting the data into a format so that we can do anything we want to at the application layer. If the CPU is still the king doing everything, it has to do this. But in a network-driven world, the NIC is responsible for all this interfacing with the outside, and the CPU is now truly just an application-specific worker node. It does the application-specific stuff, but the CPU is now handling the standard boilerplate protocols, network security policies, isolation and switching, etc. So those are our last things to push to our NIC as controller. It's easy to think of these things as offloads, and yes, they are a natural progression of our current offloads. But when you push all of this to the NIC and your application is already driven by high network I/O, you wind up in a position where the NIC is in charge. There's so little left for the CPU, it can now use all of those x86 cycles to do the fun stuff for software developers, C++ or Python or whatever programmability for their app. Unfortunately, the stuff we want to push to the NIC is a lot. My students have been hammering away at this back in my lab, and James and I have been talking about sort of the gap between GNU and Unix and all of the components that need to be developed to have a useful, fully integrated, offloaded stack. But we have published a vision paper on pushing the stack to the NIC last year at HotOS. With this HotOS paper, we come crashing head-on into a line of work in software systems with a trend called kernel bypassed. In the classic software systems world, the kernel performs a whole bunch of work on traffic when traffic comes off the NIC, and then it hands the data on to applications. But this results in overheads due to packet copies and syscalls. Over the past 10 years or so, software hackers have skipped the kernel entirely, letting applications interface directly with the NIC to get very high performance. This avoids copies and syscalls and gets you lots of go fast. But it also kind of throws out the baby with the bathwater because it completely gets rid of all sorts of useful features that the kernel provides for you. Not to mention that it pushes some things like TCP into the application, which is just frankly annoying for programmers. Here's an example of something we give up on altogether with kernel bypass. Problem here is sending too much traffic and not leaving enough bandwidth for the database. So administrator Alice can use TC to set a priority. Hello?
Yeah, what's wrong?
I thought I had a question.
Oh.
So Administrator Alice can use TC to set a priority, allowing the database to override Bob's traffic. Here's another example. What if Bob sets a weak password and now he's running a malicious web server? Because the kernel is interposing on all traffic, Alice can figure out what the heck is going on here by looking at open sockets or using TCP dump. These features and others are very useful, and they're enabled by the fact that the kernel can interpose on the traffic going in and out of the server, but administrators lose them when they adopt kernel bypass. But when we push the network stack into the NIC, like we've been talking about, we're pushing back control to administrators. Once again, this control is not control that lives on the CPU. This is control that's physically enforced by the NIC. However, because in software it's managed by the kernel, it fits into this hole that has been left behind by the kernel bypass literature. So this is still a very active area of work, and I hope to be sharing new components of this vision over the next couple of years. And I'm actually going to talk about one of these components, which I recently found out was accepted to OSDI, in just a couple of slides. Popping back up to the big picture again, I'd like to look forward at work, once again in my group, but also elsewhere, that will help us re-architect our servers towards letting the NIC take on a leadership role in the server architecture. One big and obvious thing is that I just outlined a ton of features, each of which are hard to implement and with good performance and memory efficiency and all of those good things that we want. I really like the flex toe work out of UW last year, for example. I think there are still a lot of software level questions about what functionality belongs on the NIC. Another researcher recently told me that he thinks process level scheduling should even be informed or triggered by the NIC. And that would be a huge and even bigger step towards giving the network control. But once again, this is something that's not my idea. It just fits into this growing ecosystem pushing towards a NIC-driven approach. On the hardware side, I've been trying to dance around the question of what kind of hardware we want to put on the NIC in this talk, but I really love FPGAs. There's probably some need for PISA in here too. What about other x86 processors? Maybe we should be looking at work like Panic out of Professor Aditya-Kella's group. Another hardware question is how we should design the interconnect on the server, the thing that connects the NIC and the processors and the accelerators. Can we make this network more NIC-centric? For example, I mentioned earlier that PCIe is constructed as a tree with the CPU at the root. But if we start seeing optical networking keep growing faster and faster, and we have terabit links coming in, no CPU is going to be able to keep up with that. At which point, maybe we should flip the tree and put the NIC at the root and the CPUs at the leaves. Finally, and this is going to be one more plug for research out of my own group, we can talk about the protocol that the NIC should use to communicate and exchange data with other processors and accelerators. Let's talk about how data is copied between the NIC and the CPU today. Today's NIC interface is explicitly packetized, assuming that all of the network operations are performed by the kernel in software. These data structures are represented as a memory pool, so packets arriving are allocated somewhat scattered in memory. But if the NIC is not transferring packets anymore, is this really a good idea? What should the protocol between the NIC and the server look like if we're transferring, say, a reconstructed quick byte stream, or a sequence of serialized but large RPC requests? My student Hugo proposes an approach called Ensō, where he argues that we should use an unstructured ring buffer in which data can be kept in any format that the NIC and application care about. The protocol for transfer just needs to synchronize the head and tail pointers, and the data is otherwise opaque. You can structure it however you want. The key idea is simple, although there are a bunch of tricky details into making it work well. But it turns out that this idea isn't just cleaner in terms of making the abstractions nicer for application developers. It also results in better spatial locality and hence better cache performance, reduced metadata transferred over PCIe, and thus better use of that interconnect, and it saves the application from wrangling data back into an application-friendly format, even though it may have already been TCP reassembled. Even when we're just transferring raw packet data, Ensō winds up enabling much higher packet I/O because of these factors. So today I touched on a bunch of case studies from my lab, but I also cited a ton of other work in the field right now. And that's really because I believe that the IO-driven architecture is the convergence of a lot of great ideas coming from lots of smart people across the systems and networking community. So there's a lot of work coming out of my group, and I'm really excited to keep moving towards the design of this IO-driven server. So just to recap, line rates are going up. Applications that are driven by incoming IO are suffering. Our servers, in response, should let the network interface card take on a leadership role and drive processing in order to effectively triage all of this incoming data. But there's a lot left to do. Thanks for listening, and I'm happy to take any questions.